All right, this lecture is going to be a review of stoichiometry. What makes something stoichiometry is typically this first unit is primarily going to be mass-to-mass stoichiometry. We're going to go from the gram quantity of some reactant or product to a different reactant or product. And remember, we could go from grams of one reactant to another reactant. We could go from a product to another product. We could go from a product to reactant. It doesn't make a difference. What links all of the substances together is the balanced chemical equation. What makes something stoichiometry is this middle step right here, which is the mole-to-mole step. This is when I'm able to convert from substance A to substance B. And this is linked by the coefficients of the balance equation. So that middle step, this is why we need the balance equation, is because we need those coefficients to do the mole ratio. And again, the mole ratio step is where we have a mole quantity of A. A is identified as the starting substance, and we're converting to moles of B, which is the substance in question. The other two steps involves mass of A to moles of A, or moles of B to mass of B. In order to do this, we need to know the molar mass of the compound, because molar mass is defined as the mass per mole of material. So because it's per mole, it's 1 mole. If there's a coefficient in front of the A or B, we do not take that into account for the molar mass. The only time we use coefficients is in the mole ratio step. So the molar mass we get by knowing the formula and adding up all of the atomic weights of those elements, and that gives us the molar mass, which is the grams per 1 mole of material. I can write that as a conversion factor of grams of A over moles of A, or moles of A over grams of A. All depends upon what the unit is. In typical stoichiometry, remember, if I have a gram quantity given, whatever unit I'm starting with, to get rid of it, I put it on the bottom and I move to my next unit on top. That will get rid of that unit, and we are converting from grams to moles in that step. So again, whatever unit is on top becomes the next unit on the bottom. All right, first problem here in this mass-to-mass. So a typical mass-to-mass problem, each arrow is a step. That'd be 3 conversion factors. So how many grams potassium chloride will it take to produce 50 grams of oxygen when it decomposes? Again, if you would rather pause this lecture, try to do the problem on your own, and then start back up and see what you get, please do, okay? Okay, so how many grams will it take to produce the grams that when it decomposes? So we are going to decompose potassium chlorate. Decomposition is given in the statement of the sentence, okay? Metal chlorates from our last lecture decompose into a metal chloride and oxygen gas. Balancing this reaction, we get what we see there, 2, 2, and 3. Once you have the balanced equation, you have everything you need to start the problem. So here we have 50 grams of oxygen. I do my first conversion factor. My first conversion factor is going from grams of oxygen to its moles. So whatever unit is on the top, grams of oxygen, that becomes the next unit on the bottom. I'm going to use the molar mass of oxygen, 1 mole of oxygen. There's 2 oxygen atoms, add that up, we get a mass of 32. Now I'm done with the grams. I've now converted it to moles. Now is the mole ratio step, which is going to allow me to go from oxygen to potassium chlorate. Again, whatever unit is on top, that's the first unit that goes, that's the next unit that goes on the bottom. In this mathematical problem, there are 3 moles of oxygen produced from 2 moles of chlorate decomposed. Not there yet because they want grams. So the last step is now to convert that mole quantity back into grams. Now we have to add up a potassium, a chlorine, and 3 oxygens. That adds up to 122.55 grams. And that would give us our answer in mass of potassium chlorate. Okay, so going ahead and doing the math, again, if the number's on the bottom, we divide. If it's on top, we multiply. Okay, so 50 divided by 32 times 2 divided by 3 times 122.55 gives us a mass of 128 grams of potassium chlorate. And again, because this is a rounded value at the end, I'm going to round to 3 significant figures whenever we have a number that we're going to round to. Okay, next problem. 1.2 grams of antimony combines with 2.4 grams of iodine. How many grams of antimony triiodide is formed? When we are given multiple masses or amounts of reactants, this is a limiting reactant problem, which means one of the reactants is going to limit how much product is produced. First step is the same. We still needed the balanced equation. So antimony is SB. Iodine is I. Okay, is any of them diatomic? Iodine is Hofbrinkel. It is also halogen. All of the halogens are diatomic. And we get antimony triiodide. Since there's a prefix that tells me this is a molecular compound, 3 iodines. And there's the formula. Now we need to go ahead and balance this. And we get the balanced equation there. Okay? All right. To do a limiting reactant problem, what we literally do is we just literally do 2 mass-to-mass problems to figure out which reactant is going to produce the least amount of product. The reactant that produces the least amount of product is the one that's going to limit the yield of the reaction, and that is the limiting reactant. Okay? So, however, when we do this, we must make sure that we go to the same substance. Since it's only one product here, it's pretty simple. For both of these, I want to convert the grams of antimony into the product. Then I want to take the grams of iodine to the product to see which one. I need to compare apples to apples, so I must go to the same substance. All right, the molar mass of antimony is 121.76 grams. Mole ratio, 2 moles of antimony. There's a 2 in front of this coefficient. 2 moles of antimony triiodide product. And then molar mass again. The molar mass of antimony triiodide adds up to 502.46 grams. The grams of antimony cancel, the moles of product cancel. We're left with grams of product. Rounding the 3 sig figs, I get 4.95 grams of antimony triiodide. Now I do the same thing for the iodine. Okay. Don't forget iodine is diatomic, so we have to double its mass from the periodic table. 253.80 grams. There are 3 moles of iodine to 2 moles of product. And the last step is the same because it's the same substance. Go ahead and do the mathematics, multiply across, and I got 3.17 grams of product. So now what is the answer? The answer is the smallest of the 2 values. I cannot produce the 4.95 because once I get to 3.17 grams, I have used up all of the iodine and I still have some antimony left over. And that's a typical question they'll ask next then is, of the 1.20 grams of antimony, how much of it is left? To do that, we would take the amount of product and we would do the top problem backwards. We would take the grams of antimony triiodide and go backwards to figure out how many grams of antimony was consumed to make that much antimony triiodide. And then if we subtract those 2 numbers, we get how much antimony is left over. Next problem are going to be very similar now. It's going to be repeat. So if you've had enough and want to go to the homework, please do. But if you want to try these problems and then log back in, you can at least check to see if you got the answers right. The oxidation of glucose is just a fancy way for saying the combustion of glucose. Okay, which is the good old biological reaction of where, okay, organisms like ourselves consume glucose to get energy. Okay, 1 gram of glucose. Again, this is a mass-to-mass problem, so it's 3 steps. The molar mass of glucose ends up being 180.18 grams. 1 mole of glucose produces 6 moles of water. The question is how many grams of water? And the molar mass of water is 18.02 grams. Going ahead and doing the math across, I get 0.600 grams. It's 0.6 right on the head with quite a few zeros after that. And again, the 0 out in front doesn't count. That's just whole position of the decimal point. You wouldn't even have to have that if you want. But zeros at the end do count as sig fig. So this number does have 3 significant figures. Okay? All right, number 4 is just like problem 2. Again, it is a limiting reactant problem. So we have barium nitrate reacting with sodium phosphate to produce barium phosphate and sodium nitrate. Okay, they're the proper ratios and amounts. To balance it going across, we end up needing to get 3 barium nitrates. That gives me 6 nitrates, so I need 6 sodium nitrates to balance the nitrates. 6 sodiums, I needed 2. And then I get 2 phosphates, I'm good. Okay, so there's the balance equation with coefficients of 3, 2, 1, and 6. All right, again, we've been given both grams of both reactants. The first one is 3.5 grams of sodium phosphate. The molar mass of sodium phosphate is 163.94. I hope these numbers are right. If not, please let me know. Okay, there are 2 moles of sodium phosphate for every mole of product produced of the barium phosphate. And the molar mass of barium phosphate is a very large 601.93 grams. So dividing by 163.94, dividing by 2 and multiplying by 601.93, we get 6.43 grams of barium phosphate produced. We'll do now the same for the barium nitrate. The molar mass of barium nitrate is 161.35. Okay. There are 3 moles of barium nitrate to 1 mole of barium phosphate, and 1 mole, 601.93 grams. Okay. You should be very comfortable with mass stoichiometry. This is something that needs to be mastered for the test and the quizzes coming up, and it should be an easy concept, something you can easily do for the test. So please get enough practice that you are comfortable with it. All right, going through and doing the math, get 4.91 grams. So again, the answer is the smaller of the 2. Make sure you identify that answer or make a statement of it. So this reaction will produce 4.91 grams of barium phosphate. And that is assuming that it is a 100% complete reaction. Okay? Now, how do we calculate the amount of excess reagent left? I kind of talked about it in problem 2. Now I'm going to actually show it to you. So we take the amount of product that can be produced okay? And what we're going to do is we are going to do and work backwards to figure out how much reactant was consumed of the excess reactant. So again, we'll use, the nice thing about this problem is we've got all the work ahead of us at the top there in problem 4. We just got to go backwards. So the excess reactant is the sodium nitrate. So what I'm going to do here is go from sodium, I'm going to do this one that I'm circling right now. I'm going to take that reaction and go backwards to figure out how much sodium phosphate is consumed once the limiting reactant is used up. So doing that problem backwards, now I got 2 moles of the sodium phosphate over the 1 mole of the barium phosphate. And then the molar mass of sodium phosphate is 163.94. So now going across, I get a value of 2.68 grams. This is the amount of excess reactant, the sodium phosphate. This is the amount of excess reactant that has been used up. Well, you'll notice above, we started with 3.50 grams. So now if I subtract, what is left is the amount of grams, of sodium phosphate that is left over once this reaction reaches completion. Now remember, the 4.91 grams that is produced in number 4, that is the maximum amount that could be produced. This is the theoretical maximum amount. We call that the theoretical yield. Ideally, if I do this reaction utilizing these chemical amounts, I'm not going to get 4.91 grams. It's impossible. Not every single molecule or atom will react. And therefore, what will often be given in problems, and some of your homework problems will include this, is they'll give you the actual yield, how much is actually produced. The 4.91 is the maximum amount. So if I take the amount that we actually get, the laboratory or experimental yield, and divide it by the amount that I could get, and multiply by percentage, that gives me my percent yield. Percent yield is how much of the maximum did we actually get when we did the physical experimentation. All right, that's a quick review and rundown on stoichiometry. I don't want to bore students. Some of you are pretty good at this and you still remember it, but you've got to do a bunch of practice problems now. So the more problems you do, the better. I've attached some practice problems as homework that I'd like you to go ahead and do and try. And then if you have any questions on stoichiometry, again, textbook is great, but also get a hold of me as soon as possible. Again, thanks for listening.